Okay, let us do some examples and see what does it actually look like to do the Jacobi and Gauss-Seidel methods. Okay, right. First of all, we're going to have a square plate, so I'll try and draw that. And it's to be 4 to 4, so I'll do 8 centimeters here, 8 centimeters here, 8 centimeters up, and 8 centimeters across. Okay. Now I'm not going to do all this, and I have to be careful that I do it properly. Okay, so it's 4 by 4, so that means I can go halfway down, and then also 1/4, and like this. Grid along this way. And we also want to draw grid lines in the other direction. And now doing this by hand is grand, but really it's in the VBA lab that this will make a lot more sense. Okay, what have we got? 100 is the boundary temperature on top. So all along the top it's 100. What I'm going to do is I'm just going to write this is 100, this temperature is 100, this temperature is 100. 50 to the right, so these are all 50. Yeah, sure, let's just do it this way. 50, 50, 50, 0 on the bottom, 0, 0, 0, and 75 to the left. Now I just have to check these, what my labeling. So it says take T1 to be the temperature at the bottom left grid point. Right, well anyway. So I think the idea here is that if you wanted to do this in VBA with an array, this would probably be the way to do it. I just need to have a little look that these things actually make sense. No, they don't, or they do. Look, we'll see what happens. Hopefully this, see, the issue is I've just got some output on the next page, and I want the labeling to be consistent, because you can label however you want, but will it be consistent with this? I mean, you could just do T1, T2, T3, T4, T5, T6, T7, T8, that's absolutely fine. But I think to hopefully be consistent with what's going on, we'll use something else. So hopefully this works. So the temperature here we'll call T11. Temperature here we'll call T2 along the x, 1 along the y. This we'll call T3 along the x, 1 along the y. And now we continue in this fashion. So this would be temperature 1 along the x, 2 along the y. I suppose a small remark at this point is, if it's a square, it doesn't actually matter the size of the plate as long as the grids are square. That doesn't actually come into it. So like there's no units on the 4 by 4. T2, 2, and this is 3 along the x, 2 along the y. This is 1 along the x, 3 along the y. This is 2 along the x, 3 along the y, and this is temperature 3, 3. So a good check is that 1, 2 should be hotter than 3, 2. 1, 2 hotter than 3, 2, check. And 1, 3 hotter. This is a check for me rather than you. Yeah, okay, so I think this is good. Right, so what we need to do now for this is, now to do this by hand, like it's a bit annoying. You've got 9 unknowns, 9 equations and 9 unknowns, which is a bit of a disaster. This is kind of set up for VBA but an array, but what we'll do instead is I'll just go along the bottom row just to illustrate. So temperature 11, the equation for temperature 11, it'll be the average of the 4 temperatures adjacent to T1. So going from 12 o'clock, we have T12 plus 3 o'clock T21. This 0 is not included, only the ones that are adjacent in this sense are included. Plus 0 plus 75 divided by 4. Not too bad. Next one, T21 will go in the same orientation from 12 o'clock and we'll go clockwise. T22 is adjacent, plus T31 is adjacent, plus 0 here is adjacent, plus T11 is adjacent. All divided by 4, and we'll just do one more. T31 equal to, so what's adjacent to 3T1? We've got T32 plus 50 plus 0 plus T21, all divided by 4. Okay, now I'm going to try and describe. Now the problem is I'm supposed to write down 6 more equations, so this explanation isn't full. So what you do is as follows. You come up with what we call, say, T0, which is an initial approximation. Now T0, it's a vector because it includes 9 temperatures. Okay. Now what you do is, and this is something that you mightn't have quite noticed with Bob, but it's the way I'm going to do it, it's much easier, is you take those initial approximations of the 9 temperatures and you put those approximations into these equations. And you get out new approximations. So this would be T1. And this is the second, well, we'll call it the first iteration. So you have these temperatures, initial approximations, you put them into the equations and you get out a second iteration. You get out, then you get things out. Then you take those and you feed all those temperatures back into this again. This is the second iteration. And then you keep on going, say to Tn, this is the nth iteration. And if the associated linear system is diagonally dominant, and this does come from a diagonally dominant linear system, we would have said 2 lectures ago, these converge, and they converge to the solution. So let's see a little example of this. It'll actually make more sense in VBA. Oh yeah. We won't worry too much about relaxation. That's just kind of maybe an extra thing you might want to do in your VBA, but you don't have to do it. So when we are, so this is what Jacobi's method is. I actually just described Jacobi's method. You have initial approximation, put all those temperatures in here, and you get out the next iteration. Take all those temperatures, put them back into these equations, you get out the next iteration. Eventually this converges. What that means is, we'll see that on the next page actually. Now what the Gauss-Seidel method, which is a bit faster in general, now sometimes Jacobi is faster, but in general Gauss-Seidel is, say you're even doing this by hand or especially in VBA, and Gauss-Seidel is what you're going to do in VBA. To do Jacobi in VBA, even though it's not as good a method in general as Gauss-Seidel, Jacobi is actually harder in VBA. Gauss-Seidel is very, very easy. You'll see that in the lab. So the difference is with Gauss-Seidel is, say you've got your initial approximation, which we'll talk about on the next page, and you calculate the first iteration of T11. So you put in these approximations, T12, T21, the initial approximations, you get out a number. When you come to calculating the next iteration of T21, you look at T22 and you say, okay, I'm still using the initial approximation. T31, I'm using the initial approximation. And then when you get to T11, so the difference between Jacobi and Gauss-Seidel, for Jacobi you use the old, so you'd use the initial approximation. But for Gauss-Seidel you say, hang on a minute, I've just calculated the next value of T11, which is more accurate than the previous one. So why don't I put in the very latest? So Gauss-Seidel says you put in the latest. Now you should be concerned following differential equations about mixing up previous values and next values, but these intermediate iterations don't actually mean anything. There's no actual time element here. You're looking for, there is one value for each of these, the equilibrium temperature distribution. And so these things don't, there's no sense, they're all just approximations to the, I mean, if I write down T infinity, this is actually the exact solution. In other words, if you keep doing this forever. And so if you use the latest values, this is just going to speed up this convergence. That's all. So there's no problem with mixing old and previous. If you're doing Jacobi on VBA, you're going to have to store the previous values. So either you have, say, all these temperature values and old values, or you take them from a worksheet. But for Gauss-Seidel, you actually just write down exactly these equations. Very similar in the sense that Runge-Kutta, you just write down the equations as they appear. Here you just write this down and it'll do it all exactly. Because say if this is VBA code here, after this line is executed, the new value of T11 will be the latest, and when you write T11, it won't use the previous value, it'll use the very latest. So Gauss-Seidel is faster, more accurate, and easier to implement in VBA. Okay, let's see what I write. Okay, now one of the things that comes up here, the initial approximation. Well, what's going on with that? So to implement the Jacobi method, use the previous iteration, which as I said here, use the old one, or Gauss-Seidel, use the very latest iteration. We need an initial temperature distribution. Now, I think with Bob, because actually it doesn't matter what the initial temperature distribution is, they all, so let me just make this clear. It doesn't matter where you start, you get to the exact solution if you iterate this enough times. Therefore, probably with Bob, you just start at 0. And it's fine. Any initial configuration converges due to the fact it's diagonally down. It doesn't really matter where we start. I think it's nice to think of, well, if we start near the exact solution, it'll speed up. And what I would say is that a reasonable guess, and there's a family of guesses, so I'll tell you what I think. The first is, okay, just a blunt instrument, so maybe we'll write these down here. So the first one is just take them all to be equal to 0. So take them all to be 0. All 9 of the initial temperatures, take them to be 0. That's fine. But it'll probably, the convergence will probably take longer. I think the next level up is what I'm going to do here. Is you say, okay, maybe you say something like this. Let's look at all the boundary temperatures, 150, 0, 75. We're going to expect these temperatures to be, you know, all between 0 and 100. Why would it be hotter than 100? That doesn't make sense. Why would it be colder than 0? What if I take the average of all these? Wouldn't that be a clever value? And if you do that, and I think we do the next page, it's 56.25. So you start them all at 56.25. That's probably what I recommend here. That or 0, to be honest. 0 is lazy. It's not lazy. Well, it's lazy. Sometimes lazy is good. The other one is that you get a bit more specific. What I mean by that is, say T11, well, that's besides 0 and 75. How about you take the average of those two? I think it's 37.5. Then say T21, you start that off at, well, the only thing you know that's adjacent is 0. And look at T31, what's adjacent at 50 and 0. So maybe start off 25. So something like that. That should speed up convergence, but it's not completely necessary. I think the second one is perfectly good. Take the average of the boundaries, or if you have any kind of doubt, just use the zeros. Okay. So we have the following initial guess is we're going to take all of them. So this will be T0, all of them to be 56.25. And there's 9 temperatures. And I haven't, it doesn't, like, is this T, you know, what order is this? It doesn't, well, I'm just saying, look, we're starting them all at 56.25, whatever that order is. Okay, so now we iterate. This is going to be using the Jacobi method. just because that's what happened down here. In VBA you use Gauss-Seidel, and I won't bother with the relaxation. Okay. So we're just going to do 3 of these things, and we'll leave it at that then. So the next value of, we're going to do the next value of this, the next value of this, the next value of this. We started 56.25, 56.25, and all these ones as well. So we're using this, we're going to bang all those 56.25s into these equations. So the next value of T11, which is called the 1. So 0 is standing for initial. This 1 means that it's the next, you can say it's the first iteration, you could say it's the second approximation. So it's equal to T12, sorry, I'm reading from this now. T12, previous value of T12 is 56.25 plus previous value of T21, which is the initial 56.25, plus 0 plus 75 divided by 4, and I think I'll use 4 significant figures, and I'll probably just cheat. I'll just look down here. Oh no, I won't cheat, I'll use the calculator. 56.25 by 2 plus 75 divided by 4, 46.88. Okay, then the next value of T21. So this is actually Jacobi's method, and you would have done it with Bob. There would have been a bit more linear algebra matrices in it, but this is, I'm perfectly happy with this. I'm focused a little bit more on the applications. So the equation for T21 is the previous value of T22, which is 56.25, plus the previous value of T31, which is 56.25, plus 0. So this is the equations on the previous page, plus T11. And the previous value of T11 is 56.25. And we'll just make the note that Gauss-Seidel would not use the previous T, it would use the very, very latest, use 46.88. That's the difference between them. Divided by 4 is approximately I'm getting 42.19. Actually, one of the interesting things here, just as I write, is that with temperature, you know, by and large, it doesn't actually matter what units you use, because it's difference in temperatures that is important. Okay, anyway, previous T32 is 56.25 plus 50 plus 0 plus T21, previous T21 is 56.25 and again T21, if it's Gauss-Seidel, use the very, very latest value, which is 42.19. This turns out to be 40.63. Okay. Now we've only written down 3 of the equations, but theoretically you write down the rest of them. There's 6 more of them, 1 for each of the internal grid points, and you get this first iteration out. So what we have seen is 46.88, first iteration of that, 42.19 and 40.63. You would also find all these other values. And what you do is, so basically how do you get from one iteration to the next? Plug into, I'm going to write LDE, the Laplace difference equation. So you plug For Jacobi, put all the previous values into these. Now here I've only got 3 of them, but there should be 9 of them. And that's how you get the next one. Then you take the next iteration, say the first iteration, into the LDE to get the second iteration. And you keep on going, and this converges. Now what convergence means is, roughly, is this is actually the exact answers down the bottom. So this, and you know it, essentially you know it because it's settled down. So this is converged after 8 iterations. This converged after 8 iterations. This converged on the 9th. This converged on the 9th. This one actually, this is perfectly expected because the middle temperature should be the average of the adjacents. Now it mightn't necessarily come out like that, but anyway, well, it did here. That's converged straight away. This one's converged down here. This one is converged down here. This one has converged a little bit earlier, and this one has converged a little bit earlier. It's nice and symmetric. Convergence means that, like, if you look at the 8 and the 9th are the same. So if you bang them into the formula, just the 10th is going to be the same, the 11th is going to be the same, and as we said, this converges to the exact solution. So if it's slowed down like this, basically this is the exact solution. Now it's the exact solution to 4 significant figures, so it's actually an approximate solution, a good approximate solution to these equations, but you have to remember these equations are approximations themselves. So we take Laplace's equation, we approximate it using difference equations, and then what we do is sorry, I just have to turn off the phone there. So take the Laplace equation, approximate the equation, and then you get approximate solutions to the approximate equations, which is a little bit funky, but anyway. Okay, with Gauss-Seidel, we'd expect the convergence to happen a little bit faster because you're using the very, very latest value. Okay, let's look at the second example. Oh, we got a picture. Okay, that's good. Okay, so doing it rough. I'm doing it kind of roughly here. Just time is of the essence. I'd like to grid this up. I don't quite have the time. So T11, I'm just going to do 2 significant figures. So this is 43. T12 means 1 along the x, 2 along the y. That's up here. That's 63. T13 is up here, is 79. Next one is T21, so that's 2 along the x, 1 along the y. That's this. This is about 33. T22 is about 56. Next one up. I'm taking this off the table on the previous page. T23 is 76. Next is T31, 3 along the x, 1 along the y. That's here. That's 34. Next one up, 3232, 3 along the x, 2 along the y is 52. And then the last one up here is 70. And the external temperatures, which are given in the question, which means this is a boundary value problem. Okay, so you can see hottest up here, getting colder, getting colder, getting colder. This is the coldest point here. Okay, something like this. So that was a kind of a make you up stop your rule as such. A good question is when to stop. Note that the Jacobi and Gauss-Seidel methods always converge if the problem is diagonally dominant, so eventually the approximations get within any distance of the true value. Now when I say true value, that means the true solutions of this, which are not necessarily the same as the true grid things. If you want to make it more accurate, you need to take more internal grid points. The stopping rule that I'm going to recommend is the following: that you stop when the difference between the old and the new temperature is less than 0.0305 times the new value. So to implement this stopping rule, you've got 2 options. One is that you have a variable called temperature old. I'm not mad on that. The alternative is that you print into the worksheet, and that means you can get the old values from the worksheet. but it's up to you to do whatever way you want. So, and what you have is that for all the different temperatures that they've satisfied the stopping rule. So basically, if this, this should give it correct as 3 significant figures, which is on quick. There's loads of different stopping rules, but this is the one I'm going to be recommending in your lab. What I got here? It turns out if the temperature plate starts off a certain initial configuration, that the ith iter. Okay, you can read that if you want. It doesn't make sense at this time. Okay, well, have I got anything here? So here is a temperature situation. We're interested in the equilibrium temperature. We've got a hot spot, 2 cold edges and 2 kind of warm edges. It's in this ratio 13 to 11, which means they're prime numbers. You can't get a square grid without loads and loads of grid lines. And in fact, you get 120 variables, 120 equations. If you want to solve that problem exactly, you're in serious problem. Luckily, if this is Laplace's difference equation, you can approximate them quite easily using Jacobi or Gauss-Seidel. To get the exact solutions using Gaussian elimination, 120 variables, 120 equations. Imagine like 120 rows of Gaussian elimination. Forget about it. It turns out that this is what we get. Computers can easily approximate the solution correct to 1 decimal place. So there's a few things here. I've done conditional formatting on the final solution. So like the cold bits are dark and the hot bits are light. Maybe let's write down that this is at 20, this is at 20, this is cold, this is cold. It took 96 iterations of the Jacobi method. No problem for a computer, more or less precisely the mathematics behind software that produces 3D temperature distributions. Relaxation factor, it probably wouldn't have taken 96 iterations, or using Gauss-Seidel, it probably would not have taken 96 iterations. Okay, so in terms of actually doing one of these on a lab, what do you need to focus on? You have a square grid or some kind of grid. You make it a square grid, name all the interior temperatures, write down for each interior temperature an equation that the temperature is equal to the average of the adjacents. Get an initial approximation, and then you feed in the approximations into the equations to get the next approximation / next iteration. These things converge. And what that means is if you keep on going, get closer, they stop changing basically, they've converged, and also that these will be close, very close to the exact solution of the approximate equations. Now there's rounding, so they're approximations, but they're good ones. And then we might do, as we said at the end, maybe just write down your answer, something like this. So this is something that's better suited to VBA.